Hi, in the previous episode we discussed how to evaluate different models using so-called validation set approach. In this approach we dedicated one part of our dataset for building our models and the remaining observations for evaluating the performance of those models using observations that weren't used in the estimation procedure. And also, as we saw at the very end, is that depending on splitting our data set, those the conclusion drawn from simple validation approach may slightly vary across different sampling of our data set. And in this part of the lecture, we're gonna introduce cross-validation and leave one out cross-validation procedure. Those procedures try to address this problem that perfectly we would like to make use of all observations for estimating our models. In validation approach it wasn't possible, but in cross-validation and leave one out cross-validation, it's the case. And in this part we're gonna discuss this concept. In the validation approach that we used, we estimated one specification of the model was estimated only once, and then the quality of this model was evaluated on the validation set. In so-called leave one out cross-validation approach, we do it in such a way that we take one specification of the model that we are interested what's the true error of this model, and we estimate this specification n times, where n is the number of observations. So now the question is here, why should we estimate one model n times? Because in each estimation we use slightly different training set. In each, so for each, and below you can find illustration again from our textbook that shows that for each estimation we drop one observation, one and only one observation. We estimate our model using all remaining observations, and then we evaluate this error for this estimation using the difference between the observed value for dropped observation and predicted value. And this is one statistic. We erase this to the power of 2, and then we have MSE for this for this observation, and then we repeat the same thing additional n-1 times, but in all next iterations we drop element observation number 2, observation number 3, and so on, and overall we have n estimated models, and for each n estimated models for one model specification, and then we have basically n values of MSE for each observation. That would each observation was dropped only once, and then to compute leave one out cross-validation error, we take the average of all those squared errors. So this is more or less the intuition behind leave one out cross-validation procedure that we're gonna code right now. Now let's compute leave one out cross-validation error for the model that we discussed before, LMFit. It was MPG against horsepower. We need to use this library to get access to dataset auto. Yep. And now we want to estimate the cross-validation error of this model. Yeah, so we have one specification. This is one specification, and in using leave one out cross-validation approach, we will estimate n models. N models in this case, it will be 392 models. Yeah, and that's the plan. Oh, by the way, I forgot to mention that let's use this font. Yeah, this is the font that I recently discovered. Yeah, and here what is really nice is that it has some so-called programming ligatures. For instance, if I type assignment operator, it changes this to arrow. Yeah, and there are other things like greater or equal. It changes to something like this. So still, it doesn't replace our symbols, but it renders in a bit different way. Yeah, and it's more convenient for me. Yeah, and the ligature. Yeah, so it's very similar to ligature that you know from word processors. It's that if I type double F, instead of making small space, like you could expect, it replaced with one with combined character. Yeah, and here with assignment operator, but we also with other functions like here double equal. Yeah, it changes to very long equal sign, not equal. Yeah. So the name of this font is called Fira code. Yeah, so small digression. So we want to compute cross-validation, leave one out cross-validation error. So we can do it in this way, that we can create one large one loop. We want to repeat this from 1 to dim auto. We have two numbers. We are interested in the first number, 392. So we type this, and now in the first step, using this illustration from below, we want to use all observation except the very first one. How we can eliminate from the dataset the very first observation, the observation number I, simply by this. So here, if I type auto minus I, it will drop only observation number I. Yeah, and on this dataset, our model will be estimated. And then we want to compare what's the difference between the realized value for observation I and prediction of this variable. And now, so predicted value for observation outside our dataset can be obtained using predict LMFit, and here we provide the dataset on which we want to make prediction. And here we want to make this only on one observation, auto I, comma. Okay, and now we raise this to the power of 2, and MSE something like this. Let's do it this way. That I create a vector, that with MSE for each observation. This vector is of the length of number of observations. Yep. And now our MSE leave one out cross-validation error is simply the mean of this. Yep. It should work. We see this leave one cross-validation error when we estimated n models, and for each model, the reference point, the observation that we use to evaluate the model is different, and then it's enough that we take only the mean of those realized values. Exactly the same statistic we can compute using one command from library boot. You may need to install this library, and here there is function CVGLM that conducts cross-validation procedure for us, that we don't have to write this loop, and it does it for us. And this works this way, that first we have to provide the model of class GLM. GLM is generalized linear model, and and it nests linear models like LM, but also there are different models like logit, probit, Poisson regressions, and so long. So this GLM is more general than LM, and function CVGLM requires as input the model of this class. And here, so here first we have to provide this model that we want to, for which we are interested in the computing leave one out cross-validation error. Here notice that I provide the whole data set. That I don't make any splits. This this function will CVGLM will do it for us, and yep. And now the only thing is that we provide the data set on which we want to perform this cross-validation. So actually, I'm not sure whether this information is relevant at all. For sure, what is important for function CVGLM is that it takes formula from this function, and here we provide also the data set on which we would like to compute, this leave one out cross-validation error. So here we type GLM and fit, which is it, and let's assign the output of this to this. Okay, and now we have object at CVR, and here what is important is that here with call it is only a summary what what class of model this cross-validation error was estimated, and what is important for us is delta. This is cross-validation. This is our error. Here, notice that we obtain two numbers, and for leave one out cross-validation, those numbers are the same. So, yeah, they are exactly the same, and so we can take whatever we want. But notice that essentially, yeah, this is exactly what we computed before. Yeah. What is yeah? So seed, yeah, we shouldn't care about seed. Yeah, it's some for. It's not interesting for us, and K is here. It should be equal to 392. Yeah. K. Yeah. This is for how many splits we divide our data set, and in so-called leave one out cross-validation, we split this to 392 smaller data sets. Yeah, and for other cross-validation procedure that we're gonna discuss very soon, this scale will be smaller. Now let's organize a horse race between different models with polynomials of different degree using function CVGLM. Yeah? So let's do it this way, that we create CV error, and this is numeric. Let's consider degree in polynomials polynomials of degree up to 4. And here like this. And so in each iteration, yeah, we estimate model, we provide the class of model, MPG, which is function of horsepower with degree of polynomials up to I. Yes, so for I equal to 1, it will be linear model. For I equal to 2, it will be quadratic model. For I equal to 3, it will be cubic. Yeah, and for I equal to 4, it will be polynomial of degree 4. Data is auto here. Yeah, and so here we estimate this model, and then we use CVGLM with auto and GLM fit with changes in each iteration. Well, I want to stress this, and we don't want to save all results, but we are interested only in delta. Yeah, before, yeah, CV error delta, and we are interested in the first element, let's say, only. Yeah, here those numbers are the same, and they will be the same for all leave one out cross-validation errors. So we can delta 1. Okay, sorry, I have to turn it off. Yeah, and now so we want to save delta, the first element of vector delta, from using this function. Yeah, and we want to assign the result of this to the element I of vector CV error. Yep, it seems that this is it. Yeah. We can also print like to know which iteration is horsepower. Yeah. Let's spell this. Yeah, and here. Yeah. So this is for linear model, this is for quadratic model, for cubic, and for polynomial of degree 4. We can plot this against, okay, CV error. Okay. We see that that here there is a drop in cross-validation error. Then yeah, it slightly increases. Yeah, and yeah, so here yeah, it and actually yeah, here what we see is that the model that seems to be the best in terms of degree of polynomial for horsepower, it should be equal to 2. One very important concern relating leave one out cross-validation error is that it's computationally super demanding. Yeah, because for each model we have to each specification of the model we have to estimate n times, and while for instance for 400 observations it's not such a big deal. If we have a really large data set with millions of observations, yeah, it's essentially yeah, it's not possible yeah, to do it. Yeah, and for this reason, k-fold, so-called k-fold cross-validation approach was introduced, and philosophy is super similar, and the illustration for this k-fold in this case 5-fold cross-validation error you can find below. And here, instead of estimating n models, we estimated k models where k is much smaller than number of observations. Yeah, and most common values are either 5 or 10. And in this approach, we split our data set into k separate folds. Yeah, each observation is only in one fold, and in the estimation procedure, in this cross-validation procedure, we drop one fold and estimate we estimate our model using all remaining k-1 folds. We compute MSE for this fold, and then in the next iteration we drop the next fold and we estimate our model using the remaining ones. Yeah, so it's very from application procedure, from conceptually, this is super similar to leave one out cross-validation error, but here we can control the number of required estimation of each specification. Yeah, so let's let's code it right here. Yeah, and first we have to decide about k, and in our case let's use k equal to 5. Then for each fold we will have one measure of MSE. So we want to have MSE CV, which is a vector of 5 with 5 numerical elements, and now we have to decide how to split our data set into different folds. And actually it can be done very easily using function sample. We sample from the set from 1 to k, and for each observation from dataset auto, we assign to only one fold. Obviously, there must be replacement because our k is smaller than the number of observations. Here we have a vector of numbers, and for each observation we have index of the fold where this observation should be allocated. And now so we have this, and now we create for loop similar to for loop that we created for leave one out cross validation. Error, and so we want to estimate model, this horsepower, and here we want to use only those observations for which faults is not equal is written exclamation mark and equality, and because of my font it will change to this. False is not equal to I. So for instance, if I type false not equal to 1, I will get all observation. It will be true for all elements for which fault is different than 1, and false for false equal to 1. And this is exactly what we want to have. We want to take only those observations for which false is not I. We estimate this model, and then MSE CV for this fault will be, and now we have to take auto MPG. Now we choose only those now. So we estimated the model. Our validation set in the iteration I was all observations that for which fault is different than I. So but now when we validate our model, we have to choose those observations for which false is equal to I. We take this, and from this we subtract our prediction LM feed for those guys. For those guys, so we have to choose auto false equal to I, and here we have to, this is data set, so we have to put comma, this is data frame, this is vector. So that's the reason why we didn't need comma here. And this is our prediction, and we want to raise this to power of 2 and compute mean MSE for this fault. Okay, I computed this, and now our MSE our cross-validation mean square error is mean of those 5 guys. Yep. And this is our measure for for validation error using five-fold cross-validation. What is worth mentioning at this moment is that here there is random component coming from the fact that we randomize how we split our data set. Yes, so if our seeds are, if I set different seed than you, then those measures might be slightly different, but not too much. Okay, yeah, so this is one way to compute k-fold cross-validation error. And now, instead of using this loop, we can use CVGLM just like before. Yeah, and to do it, so we will use library boot once again, and lmfit our model. Here we have to write G because yeah, it is required for CVGLM function, but yep, mpg horsepower data equal to auto. We estimated this model, and now CV5 error. Here, so far everything is exactly the same as before. Auto. The first argument is dataset, second argument is lmfit, and then before, yeah, if we don't provide anything, then the scale will be set by default to number of observations. In our case, 392. But if we type k equal to 5, it will perform five-fold cross-validation procedure. Yep. And now, so using our method, we obtain an error at the level of 24.83 around. But here, if we type, yeah, it's slightly different. Yeah, so first we have two numbers that those numbers are not exactly equal to each other. The reason for this is that here there is some correct adjustment for bias generated by cross-validation error different than leave one out cross-validation error. You can use this, but this is the raw statistic here, and in my procedure I computed this guy over here. And now what may look quite problematic is that here those numbers before for leave one out cross-validation, my number and the number computed by by function CVGLM were exactly the same, but here they are slightly different. Why? Because for k-fold cross-validation we have this uncertainty coming from sampling over here. Yeah, so if my splits are different than splits made by the function, it may generate slightly different results. Yeah, not only this, yeah, but if I run so using my code, that was cross-validation error. Yeah, 24. Yeah, MSE CV1. let's write this down, and if I run the code, the same code once again, I will get something different, slightly different. Yeah, so it is because of difference in sampling. Yeah, and the same thing relates to delta. The same thing relates to the function CVGLM. If, yeah, this is the number from running this once, but if I run this once again, some error message, okay. Okay, let's run this. Yeah, here before I obtain before that was my number, and here this number is slightly different. Yeah, and yeah, and this is it. This non-error, I think that it comes from the fact that I assigned this element fit to new object, yeah, and there was small error. Yeah, so instead of running those two lines, I run only this line, yeah, and this is most likely the source of this this error. That's, yeah, I should have made. Oops. Okay, here, yeah. Okay, I think that, yeah, this is it. Similarly to leave one out cross-validation error, we can or conduct a horse race between different models, yeah, and I will just copy the code that we already used for leave one out cross-validation, because here we didn't provide it k, yes, so by default k was equal to number of observations, yeah, and here, yeah, we compare different models, but yeah, now we will use, instead of 392, we will use k equal to 5, and yeah, I think that this is it. Okay. Yeah, you see, still, yeah, the conclusion of our analysis is similar, yeah, but yeah, here we use this five-fold cross-validation error. Yeah, so I don't know whether you saw that this is faster or not. Yeah, but maybe, yeah, maybe it would be good to illustrate, to see exact numbers, whether this method is faster or than leave one out cross-validation. And yeah, so let's compare. So let's run this code for k equal to number of observations, k equal to 5 and k equal to 10. Why not? Yeah, and in this exercise we're gonna use package microbenchmarks. Sorry, I confused the name. Not microbenchmarks, but microbenchmark in singular. Yeah, so you may need to install this. I already did it. Benchmark. Okay, and this works this way. Yeah, that that here first we provide a name of part of the code that we want to evaluate. For instance, random numbers is equal to, here in curly brackets we provide, we simply write our code. Yeah, so this can be this random numbers uniform distribution, random numbers, normal distribution, and here this is another part of the code. And last, we provide our units, how the results should be reported. Let's use seconds, and last argument, types. Yeah, so how many times each part of the code is replicated. Let's use 1000. Okay, so if we run this, it was super fast, and this code was run 1000 times, this code as well, yeah, and then we have the whole distribution of what's the required time, median, maximum value, mean for those two parts of the code. Yeah, and in our application, we will use microbenchmark to evaluate this code for k equal to number of observations, k equal to 10, and k equal to 5, let's say. Yeah. So sorry. Our comparison benchmark, and first let's use leave one out cross validation. Here this should be eliminated in our code. If we don't provide k, then this is cross validation. Leave one out cross validation error. Second, let's use tenfold cross validation, which is equal to this code, but with k equal to 10. And last, let's use fivefold cross validation error, and here k is equal to 5. Let's use unit equal to seconds, and times, let's use something smaller than 1000. Yeah, let's use this 500, and yeah, and this is it. Yeah, so let's start running this. And now, yeah, I run this code. I run this piece of each piece of the code 500 times, because only one replication to measure how much time we need maybe not enough, because of the fact that during one run I may receive, I don't know, Facebook message, and it may slow down the computation procedure. Yeah, so to make the comparison fair, we compare all those codes many times. Yeah, and actually, now it's 20 to 7. Yeah, and I believe that it should take maybe 20 minutes, maybe. Yeah, let's see. Yeah, so in the meantime, yeah, you can sit here. I will go to do some grocery shopping. So I returned from the grocery store, yeah, and the code run is complete, and now we can our comparison. Yeah, this is result of replicating, of running each snippet of the code for leave one out cross-validation, 10-fold cross-validation, and 5-fold cross-validation. Yeah, we repeated each snippet of the code 500 times. And now we see that on average, or yeah, let's it's better to refer to median values. The median run for leave one out, it was almost 4 seconds, while running cross 5-fold cross validation procedure was 60 times faster. Yeah, so you see that, and this data set wasn't that large. So overall, k-fold cross-validation method allows us to estimate the measure of goodness of fitness for model using data, not using the estimation procedure, and yeah, it is similar to leave one out cross-validation procedure, which seems to be the perfect one in terms of statistical properties, but in terms of computational intensity, k-fold cross-validation is a good compromise. Yeah, and those and most in the practice, 10 or 5-fold cross-validation are the most so k. In most cases, people tend to use k equal to 5, 10, or 3 from time to time. Yeah, so this measure allows us to evaluate the model in fair way. Yeah, and this concludes lecture 3. And in the next lecture, we will discuss about several methods of selecting the best model using, amongst others, cross-validation procedure. Yeah, so this is it for today. Yeah, and have a nice evening. Ciao.